Assalamu alaikum, Bachu. How are you doing? We're just going to continue with our giant covalent structures, right? We're going to discuss about diamond, graphite, and sand, right? And we'll also be discussing the similarity and differences between these macromolecules, and also we'll be discussing about metallic bonding. So we will be done with our, this bonding, right? Chemical bonding, right? So after that, in the next lesson, we'll be just solving that past papers of chemical bonding. So let's discuss about these macromolecules or giant covalent structures. I'll just be using the PowerPoint presentation over here so that you could see the diagram more clearly. So, so in some substances like sand, diamond, and graphite, there are going to be millions of atoms which are joined together by covalent bonds, right? So therefore, they are known as giant covalent structures. Okay. So, and these covalent bonds do not form molecules, but they are going to form a vast network of atoms, which are known as giant covalent structures. So, what are the giant covalent structure? They are going to be millions of atoms which are joined by many strong covalent bonds, right? So basically, there are going to be many atoms, so therefore they're known as giant covalent structures, right? So even we could just predict the physical properties of giant covalent structures, as all the bonds are covalent and so many covalent bonds, right? So giant covalent structures have high melting and boiling points, all right, and they're usually hard. And what is the reason why they have high melting and boiling points? Because they have many covalent bonds, so more energy is required to break the bonds. That's going to be the marking point, right? We do not have to say that they have um, strong forces or weak forces. Okay, they have many covalent bonds, right? Now sand, that is going to be silicon peroxide or SiO₂, right? That's going to be mineral quartz. Silicon dioxide is a giant covalent structure which is made up of silicon and oxygen atoms, right? So here, if you just see, it's going to form a tetrahedral structure. Each silicon is bonded to 4 oxygen atoms, right? And each oxygen atom is bonded to 2 silicon atoms, right? So it's going to form a tetrahedral structure. Okay. So this is a giant covalent structure of sand or silicon peroxide. Okay. So what will be their physical property? It's going to be hard. It's going to be a high melting and boiling point. Okay. It's hard because of tetrahedral structure, and then it's going to have high melting point because of many covalent bonds. So more energy is required to break the bonds, right? Now, what are the allotropes of carbon? This diamond and graphite are allotropes of carbon. Okay. What is the similarity? That they both contain carbon atom, but they have, different, properties because of the arrangement of atoms, and these allotropes are different. All right. So what is the common in these diamond and graphite is going to be? They both are made up of carbon atoms, right? So different forms of the same element are called allotropes. And what is the difference in the diamond and graphite is arrangement of carbon atoms in both. Okay. So these allotropes of carbon have different properties because the atoms are bonded in different arrangements, all right, which create, different giant structures. Okay. We'll be discussing how the structure of graphite and diamond differs. All right. Now see how the different structures of diamond and graphite influence their properties. Like you cannot use, this is going to be a useless invention, that you're going to use the pencil which is going to have, which is made up of diamond, right? It's a useless invention. Similarly, you cannot have a jewelry which is going to be, made up of graphite, all right? Okay, so this is how's the structure of diamonds going to be also a tetrahedral structure, right? Like each carbon is bonded to 4 other carbon atoms, right? Forming a tetrahedral structure, just like the structure of sand, all right? So diamond is very hard, the hardest natural substance, all right? It is, and therefore it is used as a cutting tool, right? The diamond is used as a cutting tool as it is very hard, all right? And it has a very high melting point because more energy is required to break the covalent bonds. All right. So therefore, we say that the diamond has very high melting and boiling point. Diamond cannot conduct electricity. Even graphite also cannot conduct electricity because there are no mobile electrons. All right, or ions to carry the charge. So these are few physical properties of diamond, right? Which is an allotrope of carbon. All right. So tetrahedral structure. What is the similarity in diamond and sand? They both are tetrahedral. What is the difference? You can say sand is a, a compound, while diamond is a, or you can say an element, right? Is going to be an allotrope of carbon, okay, which contains same type of atoms. Okay. Now, if we're just going to discuss about graphite, so graphite is going to form hexagonal rings, all right? Each carbon is bonded to three other carbon atoms, forming, having one electron free, forming, the hexagons. All right. So as it's going to have one electron free, so therefore it's going to be good electrical conductor, right? So we can say that graphite is a good electrical conductor, therefore it's going to be used, in making of electrodes in electrolysis. And also, there's going to be the layers of, atoms between the graphite there. You can say between the layers of graphite there's going to be weak force of attraction, right? There's a gap between the layers, right? So these layers can slide over each other, therefore graphite is soft, it's not hard, right? And it can be used as a lubricant. Okay, so we can see that these layers of graphite can slide over each other, and they're going to be weak force of attraction between the layers. All right, so therefore graphite is soft and slippery. Okay, this is why we can say graphite is used as a lubricant, because there's going to be weak force of attraction between the layers. All right. As we discussed that graphite conducts electricity because it has mobile electrons, free electrons, so it can carry the charge. And graphite is the only non-metal which can carry the charge. All right, it's a good electrical conductor. All right, I hope this thing is clear. So we can say because of the property of graphite, it's a good electrical conductor. So it is used as an electrode in electrolysis, and also as it is soft and slippery, so it can be used as a lubricant. Okay, and why it can be used as a lubricant? Why it is soft and slippery? Because there is a weak force of attraction between the layers, so these layers can slide over each other. In the exam, they are not going to ask us to draw the structure of graphite, diamond, or sand, but they should know, like we should be able to differentiate between these structures. Okay, we do not have this in our, like fluorines in our syllabus, right? So this is all about giant covalent structures. Another thing that we have to do is that it's going to be, they all are giant lattice structures. All right, so they all are going to have high melting and boiling point. That's going to be the common property, right? So now we are just left with, the metallic bonding. So we will be discussing about the metallic bonding now. All right. All right. So we just say that in metallic bond, what's a metallic bond? The common error done by the student is going to be between the metals. Actually, the metallic bonding is the bonding between the metals. Metallic bond is a bonding within the metal, right? So, like, there's going to be strong electrostatic force between the lattice of positive metal ions and C of D localized electrons, right? In the metals, the valence electrons are 1, 2, or 3. So these valence electrons keep on roaming, and there is going to be the force of attraction, which is electrostatic force of attraction between the lattice, like regular repeated pattern of positive ions, and C of D localized electrons. All right. So usually in paper, structured paper, they do ask us to draw a label diagram. So you're going to draw the lattice of positive metal ions having 2 to 3 layers, and you have to show the electrons which are delocalized. Like, you do not have to show it in the and the and the fixed pattern, just randomly arranged. Okay, and do not forget to label. This is also one of the way to show it. All right, this is also one of the way to another way to show it. And also you can show the electrons by E minus. All right, or sometimes if it's going to be group 2, so you could just write down 2 plus over here, or plus 2, right, other than just showing plus, right? So metallic bonding, how we're going to define, is going to be a strong electrostatic force of attraction between the positive ions in a giant metallic lattice and a sea of delocalized electrons. Okay, whenever you're just going to talk about the forces, you need to specify they're going to be strong electrostatic force of attraction. All right. Now see, because of these, bond, the metallic bonding, there are going to be few properties of the metals. They are going to be malleable, because the metals are malleable, the metals are ductile, they can be drawn into wires, they can be drawn into sheets, right? And they are going to be good electrical conductors because they have mobile electrons, all right? So why you can say that metals are, ductile and malleable, The metals are ductile and malleable because the layers of metal ions can slide over each other when force is applied. And why metals are going to have high melting and boiling points except group 1? Because of the strong electrostatic force of attraction, just like ionic compounds, right? So more energy is required to overcome the forces. So therefore we can say that metals have high melting and boiling point. Okay. And similarly, the metals are malleable and ductile because the layers of metal ions can slide over each other. So the metals are malleable and ductile, right? And metals are good conductor of heat and electricity due to presence of you can say mobile electrons, all right? I hope it makes sense, right? So this thing is clear. That is all about, the bonding, right? One more thing that I just need to do, that is going to be, we have to compare the bonding, right? All the type of bonding that we have done till so far. So this is going to be the type of bonding in a substance that affects the structure of that substance. Um, the type of structure in ionic compound is going to be giant ionic lattice, right? Particles in structure are going to be millions of ions. And what is the state of ionic compound is solid. Covalent compounds can be simple molecular or giant lattice structure. There are few atoms in simple molecules, and in giant covalent structure, there are going to be millions of atoms, right? There are going to be simple molecules are usually liquids or gases, not solids, or volatile solids, and covalent compounds are giant covalent structures are solids, right? There is also going to be giant metallic lattice. So giant structure will be for giant covalent lattice, like you can say macromolecules, giant metallic lattice in metals, and also giant ionic lattice is there in ionic compounds, right? And there is going to be particle structure going to be millions of ions and delocalized electrons, right? So the metals state as liquid state except mercury, which exists as a liquid state. All right. So I hope that thing is clear. So this is the strong that shows the metallic bond. This shows giant covalent structures, and this shows the ionic compounds, right? So this is the simple molecules, right? So they're going to be weak force of attraction between molecules, so less energy is required to overcome these forces, right? So one more thing that you have to do is, like in metals, there are going to be the metal ions state at the fixed position. There are going to be electrons which are going to, roam around, which is going to move, okay? But the metals, you can say that metal ions remains at the fixed position, right? And then these again, I'm repeating, they're going to be mobile electrons which are going to be responsible for conductivity. Okay, there's only one animation that I have to show you regarding metallic bonding, right? Because sometimes students think that there are going to be positive ions also which are going to move around, right? So let me just show you this animated slide. Okay, so, and in the next video lesson, we are just going to discuss some past paper questions of chemical bonding, and that is going to be the one of the basic, um, chapter that you have to be good enough to, to build up your knowledge or to strengthen your concepts, right? So, I'm just going to show it. Here you go. All right, so right, so in the metals, like the positive metal ions are like stay at the fixed position. They're going to be mobile electrons, the electrons which move. Okay, see, the metal ions stay at the fixed position, the electrons are moving. All right, so that's it. I hope that these two videos are fruitful for you. See you, take care, bye.